one reason. All right, looks like we're going. Sorry for hesitating there. Do one more check. All right, looks like we're recording. Sorry for the delay. Hopefully everyone can hear me. Let me know if it looks like anything is wrong. So welcome to day 18 of operating systems class. This is where we got at the end of class last time. I had enough time to say a few words about our next topic, virtual memory. The idea here, and I showed this slide, I tried to make the point that we're going to be thinking about extending memory to let us run more programs at once, effectively to do what we've been trying to do, to let us get as much as we can out of a limited physical memory. We've already seen the memory hierarchy operating sort of at faster, smaller levels. We know that under controller compiler, we get to decide what stuff's going to get brought into CPU registers and what has to stay out in main memory. With help from the hardware, we get to decide what lives in cache and what has to stay in backing store, what has to stay in larger, slower main memory. Could we do the same thing? What if we wanted to run so many programs with so much total memory that we couldn't fit them all in physical memory, we couldn't fit them all in main memory at the same time? Could we extend this hierarchy to another level, letting parts of running programs live out on secondary storage and only bringing the parts into main memory that we need? This would let us effectively have a lot more programs running than we could fit in memory. It's just parts of those running programs wouldn't really be there in main memory. They'd live out there on secondary storage. And when I say secondary storage, I mean disk, some kind of bigger, slower backing store for main memory. And then as the program ran, maybe we would bring parts of it in and out of main memory, hopefully with help from the operating system, hopefully automatically. This is how we could think of that working, at least between these different components. Over on the left, and I'll point to it here, you could think of a process as consisting of a bunch of pages, maybe way more pages than we could fit in main memory at once, or than that process really needed at once. How about if we just brought some of them into main memory as the process was using those parts, and the others could live out there on secondary storage, could live out on disk. And then as the process tries to access parts of its memory, we'll bring in a page worth of memory into an available frame of physical memory. Then the process can use what's in that page. And if a process has a page that it's not actively using anymore, maybe we could free up that frame worth of memory by writing that out to secondary storage and then letting that frame host some other page of the process, or maybe some other page of some other process. Now, we already did this kind of trick in the form of swapping. Remember, the idea of swapping is we could take a whole program, and if it wasn't busy right now and memory was scarce, we could write that out to disk and then bring it back in later when there was less contention for use of memory. But here, with the page memory hardware, we can do this at a much more fine-grained level. We don't have to take a whole process and write it out to secondary storage. We can just do that with the individual pages of a process. And if a process is running and it only needs part of its memory right now, we could write out the parts that it's not using, free up those frames of memory, and like I said, we could let some other program use those, or we could use it to host other pages of that process. I hinted at this a moment ago. It would be great if this could happen automatically. We mentioned that historically programs have used things called overlays to bring in parts of their code as they run and to replace in memory old parts of their code that they're not using anymore. Any program that runs kind of in phases like a compiler, maybe once it's done with the preprocessor, it could use that memory to host a different stage of compilation. But that required work from the programmer. It would be nice if the OS could do some of this for us without us having to write special code to do this. So we really want to build a system that supports demand paging. The idea of demand paging is processes could automatically have pages that they use out on secondary storage. And then when they try to access those pages, and here's where I should have said automatically, whenever they try to access a page, the OS could go get that out of secondary storage and then bring it into an available frame of memory. That means a process would have some of its pages living in frames of main memory or physical memory, and hopefully a lot of its pages that it's not actively using right now could live out there on secondary storage, not taking up space in main memory. So some pages will be what we call memory resident. They'll live in a frame of physical memory. Some pages won't be memory resident. They'll be out on backing store. And then when a process tries to access a page that's not memory resident, it would be nice to, and this is kind of what we're working toward, it would be nice to have a mechanism so that the OS can do that automatically without the programmer needing to write code for that. Whenever a process tries to access a page that's not memory resident, the OS will notice that it's not in memory. It'll go get it out of secondary storage and bring it into memory. And that's the idea of demand paging. As a process tries to access pages that are not memory resident, it's trying to use that page, the OS will automatically go bring that in. I've been really talking about these next two words, page in and page out. And that's just the mechanism for moving pages between main memory and some backing store, typically on secondary storage. Predictably, page out is when you've got a page that a process isn't actively using right now. Maybe we could free up that frame of memory by writing that page out to secondary storage and then using that frame for something else. That's paging out the page. Paging in is the other way. When a process tries to access a page that's not memory resident, the OS will page it in, it'll copy it from secondary storage to main memory, and then the process can resume running and use that page. Demand paging just says we'll bring pages into memory whenever a process tries to access them, if they're not already memory resident. Pure demand paging, that term down at the bottom of my slide, that just means the only time we will bring a page into memory is when a process accesses it. What's the difference? With pure demand paging, when a process starts running, we won't even load that whole process into memory. Maybe we'll just load the page that contains main into memory. And then as the process tries to access pages that aren't memory resident, when it first tries to access that page, that's when it'll get brought into memory, but we won't load pages into memory until a process tries to access them. This could have some advantages. It could give us faster process startup. We just have to load pages as a process uses them, so we don't have to load all of the load image for a process at startup. And like we talked about with demand loading, if there were parts of a process that it never actually needed, at least on a particular execution, maybe some error handling code or some code for a special case, we might never actually have to load those into memory, which would let us get more use out of a limited physical memory. Questions before we move on. So the trick we're trying to do is, with help from the page memory hardware, we're trying to provide processes with a lot of the advantages of demand loading and of, I guess, mostly demand loading without extra code from the process. I asked if people had questions and then I kept talking. Any questions at this point before we move on? All right, the nice thing is we're going to be able to do this without any additional help from the hardware. We kind of planned ahead, and when we were talking about page memory hardware, we built in mechanisms into that that let us do this with help from the OS, but without much extra work from the process. So we said demand paging is the idea that when a process tries to access a page, if it's not memory resident, we want the OS to go get that page out of secondary storage and bring it into main memory, bring it into an available frame of memory without any extra work from the process. How are we going to do that? Well, like I said, that's just going to require using the page memory hardware kind of in a new way. When a process tries to access a page that's not in memory, how is the OS going to know that it tried to access a page that's not in main memory? We're going to do that with the valid invalid bit. Any page that's memory resident. In the page memory hardware, there's a picture on the next slide. I'll jump ahead to that and then we'll go back to the previous slide. But any page that's memory resident, well, it'll have a frame that it lives in main memory, and the process that owns that page, it'll have a page table, and any page that's memory resident will have the frame number where that page lives, will have the frame number where that page lives, and it'll be marked as valid. So if the process tries to access that page, it can access it without any help from the OS. Pages that are not memory resident, we'll mark those as invalid. Why? Well, they're pages the process should be able to access. But if they're not memory resident, if they don't really live in a frame of memory, then as soon as the process tries to access it, we'd like the OS to find out about that so it can go get the page off secondary storage and bring it into a frame of memory. So all the non-memory resident frames are going to be marked as invalid. Again, not because the process shouldn't access them, but because when the process tries to access them, we want the OS to find out about it right away. So we're really building the page table so that the hardware automatically notifies the OS via a trap whenever a process tries to access a page that's not memory resident. I don't think I mentioned this term. When that happens, we'll call that a page fault. If a process tries to access a page and it's out on secondary storage rather than in main memory, we're going to trap to, at least we'll, using the valid invalid bit, we'll make it so the hardware traps to the OS when that happens. And then that's when the OS will page in that page. Really, this means whenever a process tries to access a page that's invalid, the OS has to make a choice, or at least it has to figure out something. It has to decide, well, the page you are trying to access, is that even a page that you should be able to access? Maybe you're just accessing an invalid memory address, address that shouldn't even belong to that process. If that happens, same as always, we might kill the process and say something like a segmentation fault when that happens. So a process could still get terminated if it accesses an invalid page, but now we need support for this new behavior. Maybe that page was only marked invalid because that page isn't memory resident right now. When that happens, the OS is going to have to do some work. It's going to have to go get that page and bring it into memory. So I think I've covered everything on this slide. We already looked at this picture. This describes, so this list of steps describes what the OS is going to have to do when a page fault occurs. I'll read through this list quickly and I'll try to make each of these steps make sense. These steps correspond to this next picture on the slide. This is a picture on the slides. This is a picture out of your book that kind of illustrates all the stuff the OS has to do when a page fault occurs. We'll look at this picture again real quickly, but all the numbers on this picture, like step 1, step 2, step 3, I tried to make those correspond to the steps I put on this slide. So when a page fault occurs, when a process tries to access an invalid page, well, the hardware is automatically going to trap to the OS when that happens. That's what happens when a process accesses an invalid page. And like we just said, the OS has to figure out, is that a page that you shouldn't be able to access? In which case, we're going to terminate the process or send a signal to it or something like that, depending upon the OS. Or if it's a page that's on backing store and just isn't memory resident, then we're going to have to page in that page. Down on step 3, we say, well, we got to find an available frame. So hopefully there's a frame of memory that doesn't have anything in it. We'll bring the page into that frame. We're going to have to block the process while this happens. Or at least if it's a multi-threaded process, we're going to have to block the thread that page faulted because it's trying to access something that isn't in memory right now. And until we bring that into memory, we're not even going to be able to complete the current CPU instruction. So as we're servicing the page fault, the process or thread that page faulted is going to have to be blocked. So we'll block it and we'll put it on a scheduling queue, maybe waiting for the disk drive or wherever our backing store, wherever our secondary storage is for holding pages that aren't memory resident. The OS will schedule I/O to bring in that page. So if we're bringing it off of disk into main memory, that's I/O. It's just not I/O that the process really asked for. It just tried to access some of its memory. So the OS will schedule that I/O. And like any I/O operation, that's going to take a while. While that I/O is happening, the OS is going to do what it would normally do. It's going to let another process run on the CPU. So a page fault is kind of like any other I/O operation. The processor thread that page faulted gets put in the waiting state. It gets blocked. It's waiting for I/O to happen. It's just I/O that the process didn't really ask for. It's I/O that's necessary to bring the page that it wants to access into main memory. So while that's happening, again, just like any other I/O, some other process from the ready queue will probably get a chance to run. That's what my little note over here on the right means. When I say imagine elevator music, I'm saying that's going to take a while that page is being paged in, so the OS will probably do something else with the CPU. Once that I/O operation is done, down in item 5, the hardware typically will interrupt the OS, will interrupt the CPU, letting the OS know that a scheduled I/O operation is done, and that's when the OS can get ready to resume running the process that page faulted. It can put it back in the ready state. Well, first it's going to fix up its page table. So that page that used to be marked invalid, well, now that it's been brought into memory, it's valid. So we'll set its bit in the page table to be valid. We'll fill in the frame number to say what frame it lives in now. And now the process is ready to resume running. We can mark it as runnable and put it back in the ready queue. And then whenever the CPU becomes available or whenever it gets its turn based on the CPU scheduler, it'll get to resume running. It'll effectively rerun the CPU instruction that caused the page fault. And then as long as all the pages it needs are memory resident now, it'll be able to complete that instruction and keep on running. So these are, I think of them as the typical steps that happen in the hardware and mostly in the OS when a page fault happens. This is a picture that shows kind of what we talked through. I'll say it real fast. Page fault happens, we track to the OS, it finds an available thread. Page fault happens because the process tried to access an invalid page. We track to the OS figures out, oh, you should have that page, it's not memory resonant. Let me schedule some I/O to get that page off of disk and bring it into a free frame of memory. And then once it's memory resonant, once that I/O operation is complete, we'll fix up the page table so it says what frame that page lives in now and marks it as valid. And then I can rerun the CPU instruction that tried to access that page. Now, this picture assumes that whenever you try to access a page, there's an whenever you page fault, there's an available frame to bring that page into. And that's going to be true if memory is abundant. But if memory is scarce, you may have all of your frames full of pages, and there may not be room to bring a page in. That means servicing a page fault is really going to be a two-step process. If you want to resume running the process that just page faulted, you got to make room to bring that page in, which means typically you're going to have to kick something out of memory to make room for that new page. The OS is going to have to pick, if memory is full, then whenever we bring in a page, we're going to have to throw out a page, hopefully one that isn't being actively used anymore. We'll call that the victim page. Again, if memory is full, whenever a page fault occurs, the OS is going to have to pick a victim to throw out of memory before it can bring the faulted page into memory. just to make room for that. This is going to make page replacement, or sorry, this is going to make a page fault even more expensive, because now we need two IO operations. At least we might. If memory is full, we have to pick a victim, we have to page that out. Well, that's an IO operation. And then we have to schedule IO to bring the faulted page into memory. So that means every time a page fault happens, it's really going to slow down the execution of that process. Hopefully, page faults don't happen that often. As a process runs, hopefully it's accessing a small number of pages over and over and over again before it starts trying to access different pages. Whenever it starts accessing a page that maybe it's never accessed before, or maybe it hasn't accessed in a long time, that's the kind of thing that's likely to generate a page fault. Well, this, like I said, this could really slow down the execution of a process, but that would depend on how often the process page faulted. We could pretend that we knew that in the form of a page fault rate. That would be on a memory access, how likely is that to page fault? So the page fault rate, I think that's a row there. I'll just call it a P because it looks kind of like a P. Page fault rate would be some fraction between 0 and 1, 0 meaning a process never page faults, 1 meaning a process page faults on every memory access. If we knew the page fault rate, we could compute the effective memory access time based on how long it takes to access memory when there's no page fault versus how long it takes to access memory when there is a page fault. And that would just be a weighted sum of how long it takes to access memory under those two scenarios. So if we knew the page fault rate, then whenever a page fault doesn't occur, well, that's going to cost us the amount of time it takes to just access memory. So again, if P was our page fault rate, then whenever a page fault doesn't occur, that would be 1 minus P times how long it takes to access just plain old main memory. And again, I probably skipped saying this. If we wanted to compute effective memory access time, it would just be a weighted sum of how long it takes to access main memory times how often that happens. That's what we just did. Versus how long it takes to service a page fault times how often that happens. Well, P is how often page faults happen. And when a page fault happens, just like we said, there's a lot of stuff that has to go on. The hardware has to trap to the OS. So let's call that page fault overhead. How long does it take to trap to the OS, for the OS to pick a victim page, and then to schedule an IO operation to page out the victim? So how long does it take to page out a victim page? And then we've got to schedule an IO operation to page in the page that got faulted. So plus however long that takes. And then once that IO is done, the OS has to fix up the page table and then put the process back in the ready queue. So however long that takes. And then finally, a process gets to access the memory it was trying to access. So whatever time that takes. We could make up plausible numbers for this. Let's say if you tried to access main memory, that cost 200 nanoseconds. And that's kind of ignoring the benefit of cache. And that number's probably a little old by nowadays standards, but there I'm assuming you really have to go to main memory. On modern hardware, you have to think about whether or not you got a cache hit or a miss. And if you got a cache hit, you'd be doing way better than this. But for now, let's just assume that you have to go to main memory on when you don't have a page fault. When you do have a page fault, well, you have to do all that other stuff. If you back up, I listed all the other stuff here that the OS and the hardware have to do to service a page fault. But backing up, these two are really the most expensive. The IO operation for paging out a victim and for paging in the faulted page, those dominate all these other costs by quite a bit. So let's say when a page fault occurs, all of that IO takes 8 milliseconds. So 8 thousandths of a second, which doesn't sound that bad, until you compare it to nanoseconds. So if we rewrite that in terms of nanoseconds, 8 milliseconds is 8 million nanoseconds. And you can see, so when you don't get a page fault, accessing memory is comparatively cheap. When you do get a page fault, accessing memory, at least the cost of that one memory access, is way worse, 8 million nanoseconds, at least in these made up examples. So what if you had a page fault rate that was pretty low? Let's say on memory accesses, 99.9% of the time, you don't have a page fault. And only 1/10 of a percent of the time, you do have a page fault. That doesn't sound too bad, but if you compute the weighted sum we just did on the previous slide, 0.999 of the time, you get 200 nanoseconds, and only 0.001 of the time, that's your probability of getting a page fault, so 0.001 times the 8 million nanoseconds, that works out to an average or an effective memory access time of 8,200 nanoseconds, which means a page fault rate of only 1/10 of a percent would make your computer run 41 times slower. And I'm going to say that's too much. We can't afford that. I don't think we want to give up on virtual memory. That would get us a lot more use out of a limited physical memory. But I think the takeaway here is we need a page fault rate that is way, way better than one page fault every 1,000 memory accesses. We need a page fault rate that's one every 100 million one every 100 million memory accesses, or better than that. How can we get this? Well, what control does the OS have if the OS is trying to maintain a low page fault rate? There's only so much the OS can do for this, and I've kind of listed those things here. The OS gets to decide how much memory each process has, how many frames it's going to let each process use. And we'll say this again later, but in general, if a process has more frames to work with, if you give each process more memory, you would expect it to page fault less often because it can keep more of the stuff it's actively using in memory. So that is one control the OS has. It also gets to choose who the victim is. We mentioned this before. If memory is full, then every time we page something in, we got to page something out to make room for it. And the thing we page out, we call that the victim. The OS does get to pick who the victim is, what it's going to throw out. And I guess in picking a victim, we would like to pick a page that isn't being used that much. If you think of your memory as having pages that are being very busily used or actively used by processes, versus some frames could contain pages that nobody's using right now. Those idle pages make good victims. So we need a good way to let the OS choose idle pages, or ones that it looks like nobody's actively using. The OS does have one way of making this choice for a victim, victim selection policies. And later on my next slide, we're going to call these page replacement policies. And that's what I started to say a moment ago. They can be either local or global. Local means when a process page faults, one of its own pages gets picked as a victim. So if you access a page that wasn't in memory, if you're using all of your available frames, then the OS is going to pick something of yours for a process. If you're a process and you access something that wasn't in memory, something that wasn't memory resident, the OS will bring it into memory, but it'll have to pick something else of yours to throw out to make room for it. That's a local policy versus a global policy, which says if you page fault, any page of any process could get picked as a victim. So if there's some other process that has a lot of frames that it's not actively using, maybe those would make a better choice as a victim. And we'll revisit this later. It's worth knowing now. But later we'll see there are some advantages to local and there are some advantages to a global page replacement policy. No one's had a question yet. As always, even if I'm talking, feel free to interrupt me. if you have a question or if something I'm saying doesn't seem clear. I also try to pause occasionally to invite questions. Are there any questions? Three 1,000. All right. So this is what I mentioned on the previous slide. We got a fancy name for the OS's rule for choosing a victim, and we call that the page replacement algorithm. When I have to bring something into memory, I have to throw out something that was in memory, at least if memory's full. So it's kind of like every time I bring in a page, I'm replacing a page that was in memory with that new page. So we want the OS to have an effective victim selection policy. We need it to have a page replacement policy that tries to minimize page faults. Because like I said, the OS doesn't have a whole lot it can do to try to reduce how often page faults happen. But we already saw if page faults are happening even 1 out of every 1,000 memory references, that's way too expensive. So we're going to look at different ways the OS could implement a page replacement algorithm, kind of like we did when we were talking about CPU scheduling. These are all going to be kind of good ideas that we might want a page replacement algorithm to try to emulate. And we'll end up talking about realistic, at least a realistic page replacement algorithm that kind of tries to take advantage of a lot of those good ideas. To look at individual page replacement algorithms, we'll pretend that we know something about the memory access pattern of a process. We'll pretend we know something about the pages it's going to want to access, and we'll call that a reference string. That's really just a sequence of pages that a process is going to access. And I'll jump ahead a couple of slides to show you this. That'll be something like this. Here's a made-up reference string. And you can think of this as saying, well, a process wants to access something on page 1, then something on page 2, then something on page 3 of its logical address space, then something on page 4, and then something on page 1 again. Maybe not the same thing it accessed back here at the start, but as long as it's on the same page, that's all we care about for page replacement. If this page is in memory, then it ought to be able to access any byte, any location on that page, as long as it's memory resident, even if the byte it's accessing here isn't the same byte it accessed here. So for a reference string, we're looking at the memory access pattern of a process, but only a page at a time. We don't really care about which particular byte, which particular offset within that page. So a reference string is just going to be a sequence of pages that we're pretending a process wants to access. Given a definition of a page replacement algorithm, as long as we understand how it's supposed to work, we can see how it would behave on a particular reference string. And we'll do that for a few simple page replacement algorithms. Now, here's a graph out of your book that shows something we can expect. And that is, and we said this already, if the OS gets to decide how many frames a process has to work with, how much room it has in memory to host the pages that it needs to access. And if we give so this graph says, if we give a process more frames, we can expect it to exhibit fewer page faults. That's what this blue line represents. And I'm going to say this is an idealized graph. This is just a made-up graph showing what we expect. So horizontally, we're showing how many frames we give the process. So over here, we're pretending we give it more frames. Over here, we're pretending we give it fewer. And this vertical axis, we're pretending that shows either the number of page faults or informally how often it page faults. So if we give it a bunch of frames, well, here we're pretending 5 is a bunch. In practice, that's tiny. You would give a process way more frames than that. But to make it easy to talk about, if we gave it several frames, it's not going to page fault as often. But as we give it fewer frames, as it has to fit the stuff that it's using into a limited amount of physical memory, as we make that limit lower, it's going to have to swap out what's in that memory more often, so it's going to exhibit more page faults. All right, that's what we expect to see. Let's try out really the simplest page replacement algorithm I could come up with. And that is, well, I didn't come up with this, but it's the simplest one that we could probably think of. And that is first in, first out. We'll abbreviate this as FIFO, but it just says replace pages in queue order, in FIFO order. And that means whenever a page fault happens, we're going to have to, if memory is full, we're going to have to throw out something that was in memory. FIFO would say throw out the thing that was brought into memory the longest ago in the past, or throw out the thing that's been in memory the longest to make room for the new thing that has to get brought into memory. Here, we're going to simulate FIFO on this reference string. So like I said before, we're pretending this reference string means a process accessed something on page 1 of its address space, then page 2, page 3, page 4. And then, like processes do, they reuse pages. So then maybe it wanted to access something on page 1 and then page 2, and then page 5, which it hadn't used up to this point, and then the rest of the reference string. So we're going to try out FIFO on this reference string, and we're going to see what gets brought into memory. For all of these examples, we're going to assume memory is initially empty. Or what I mean is, we've started up this process, and none of its pages have been brought into main memory. So as it accesses them, initially, it's going to get page faults. And I'll try to set this up so I can draw right on my slide. And I'll try not to make any mistakes as I'm doing this. All right, so we're pretending nothing is in its frames of memory initially. So they all, say they start out empty. Realistically, they have, whatever used to be in that frame of memory, but nothing that this process wants. So when it accesses page 1 of its address space, that's not memory resident. So we're going to have to break. So that's going to trap to the OS. The OS will service that page fault. It'll schedule I/O to bring page 1 into memory. And that just cost us a page fault. So I'll keep a count down here of page faults as I simulate this algorithm. So that's one page fault so far. Back up at the reference string, it accesses page 2. That's not memory resonant, so we'll bring it into the next frame of memory. And that cost us another page fault. So I'm counting page faults down here using tally notation. It accesses page 3 of its address space. That's not in memory, but I've got an available frame. So we'll bring it into the last frame. So on all of these, we'll fill up the frames top to bottom. And if I ask you to do some examples like this, I want you to do it the same way, and that'll make sure the results you get match the results I get. I'll give you a reminder about that if you have to do an exercise or an exam question about that. Before I forget, we just brought 3 into that last frame of memory. So that cost us another page fault. Questions so far? All right, we're up to here in the reference string. Then the process accesses page 4. That's not memory resonant, so we're going to have to bring it in, but memory's full. So we have to pick a victim to throw out. And FIFO says pick the one that's been in memory the longest. Well, page 1 up here was the first thing we brought into memory. So that's what we're going to throw out. I'll just put an X through it, and then we'll bring 4 in its place. And I'll just write the 4 out here next to that slot, rather than trying to erase this. And that cost us another page fault. So we're up to 4 page faults so far, and we're this far in the reference string. And next, the process accesses page 1, which I feel kind of stupid, because that was in memory and we just threw it out. But FIFO doesn't try to keep up with that. It threw out the page that's been in memory the longest, and here that was just a bad choice, because the next thing we need is page 1. So we need to bring it back into memory. We need to throw out the thing that's been in memory second longest, or among the pages that are in memory now, which one's been in memory the longest? Well, 2 is the one that's been in memory the longest. So we're going to throw it out. to bring in page 1, and that cost us another page fault. So that's 5 page faults so far. We're up to here. The process accesses page 2, and again, that was just in memory, but we threw it out. We need to bring it into memory, and it's going to replace page 3, the one that now has been in memory the longest. So we throw out 3, we bring 2 in its place, and that was another page fault. Now we access page 5. It's not in memory. We need to bring it in. Now we're going to have to throw out page 4, and you can kind of see the nice thing about first in, first out, as far as simulating it and for implementing it, is it's really easy to implement. You're noticing as I throw out pages, I'm just going to go top to bottom in this. If I filled in the frames top to bottom, then every time I throw out a page, I'm going to be doing the same thing. I'm going to throw out page 4 to make room for page 5. And then the next victim is going to be this page 1. So I'm just cycling through the frames of memory in order. Whenever I need to pick a new victim, it's just going to be whatever's in the frame after the previous victim. So implementing, choosing the next victim, is computationally very cheap. I could implement it by just having a pointer to whichever frame is going to be the next victim. All right, so we were back here. We referenced the 5. It's not in memory, so we're going to throw out the 1 to make room. I made a mistake there. I think I had already partly marked through this 4. At some risk, I'm going to start this example over again, and I'm not going to take that side trip I just took to, all right, so I'll try and do this faster. So you'll recall the example we just did, and if I had an eraser, this would have been easier to do, but I kind of lost track of what I was working through. So we access page 1, page 2, page 3. Those were 3 page faults, so 1, 2, 3. And then we access page 4. We had to throw out 1 to bring in page 4. That was a page fault. And then we access page 1. We had to throw out page 2 to bring in page 1. That was a page fault. Then we access page 2. We had to throw out 3 to bring in page 2. That was another page fault. And then, I apologize, I might have messed this up in talking through my example before, so I'm glad I got a chance to go back and redo it. All right, so we're up to here. We just accessed page 1, and we accessed page 2. Now we access page 5. Yeah, I messed this up before, or at least I was about to. We throw out page 4. It's the one that's been in memory the longest, and then we bring in page 5. And that was another page fault. Then we access page 1 over here, and when I'm doing this in class, at that point, I normally try and do a Homer Simpson, woohoo, because that is memory resonant. I think this is the first time that happened. We access page 1, and it's right here in memory. So that's not a page fault. We access page 2. It's right here in memory. So that's not a page fault. So those 2 accesses are going to be cheap. We access page 3. Now that's not memory resonant. So we're going to throw out page 1 to bring in page 3. Now that's another page fault. We access page 4. It's not memory resonant. So we throw out page 2 to make room for page 4. That's another page fault. And then we access page 5. It is still in memory, so that doesn't cost us a page fault. So we made it all the way through the reference string, and we ended up with, if you look at our counter down here, there's 5 plus 4 more. So we ended up with 9 page faults. So this particular reference string, if we had 3 frames of memory to work with, it's going to generate 9 page faults. And that's, I mean, thinking of those as realistic numbers, that's way more page faults than we want. We're working tiny examples here. And on a realistic system, you would have way more frames to work with. And realistically, a process would be using way more than 5 pages of memory. We're just working small examples to see how these algorithms work. I said, any questions before we try the next example? And I apologize for having to restart this one. All right, we said in practice, a process would have way more frames than this, and it would be accessing way more pages of memory. What if it did have more frames? What if we gave it one more frame of memory? We would expect it to be able to make good use of that. We'd expect to see fewer page faults. So let's give that a try. Same as before, same reference string, but now we're giving the process one extra frame. It's got 4 frames to work with. We're kind of pretending the OS is letting it have a little bit more of main memory to host its pages. What would happen given this extra frame of memory? Well, we can run the same simulation. So when it first tries to access memory, in fact, for these first 4 accesses, they're not in memory, so we're going to access page 1. It's going to get brought into the first frame. Page 2, it's going to get brought into the next, then page 3, and then page 4. That was 4 page faults, but instead of counting them down here like we did last time, I was counting them with tally notation. I'm just going to use what I write in these slots in the page table. In the previous example, I deliberately counted them in the corner to call attention to when a page fault happens. But every time a page fault happens, we're having to scratch out what used to be in a frame and write what we bring in the slot next to it. And that really is keeping a count of the page faults for us. You can see we've already had 4 page faults because we brought 4 things into memory. And then the next page fault is going to replace this one, and we're going to write something out next to it. We can just use that to keep up with when a page fault happens. All right, so we already had 4 page faults. And then the process accesses page 1. Woohoo, that's in memory, so that's not a page fault. It accesses, and remember, these were page faults when we had less memory. It accesses page 2. That's not in memory, so that's not a page, sorry, that is in memory, so that's not a page fault. Then it accesses page 5. That's not in memory. So like I said, we have to throw out page 1 to bring in page 5. That cost us a page fault. And then when it accesses page 1, we're feeling kind of stupid because that was in memory, but we just threw it out. So we have to page fault to bring that in. We're going to throw out page 2 to bring in page 1. Then we can access it. Now then we access page 2, which again, we're feeling kind of stupid because we just threw it out of memory. But we'll throw out the page that's been in memory the longest to bring in page 2. Then we access page 3. Now we're going to have to, it's not in memory, so we're going to have to throw out page 4 to bring in page 3. Then we access page 4. And that's not in memory, so we throw out page 5 to bring in page 4. And lastly, we access page 5. And again, it was just in memory, but we threw it out. We're going to have to throw out page 1 to bring in page 5. If we count up page faults, like I said, we can count them up by seeing every time I wrote down a new number. So that's 4 in this column, plus 4 more for 8, plus 2 more for 10, which is a little bit of a surprise. Because if we back up to our previous example, when we only had 3 frames, we got 9 page faults. And we would expect having more frames of memory would let you have fewer page faults, and normally it does. But I lied to you. I lied to you when I said this is a random reference string. Well, it looks kind of like a random reference string, but this is really a carefully designed reference string that shows that this can happen. And the this that can happen is having more memory can actually reduce performance. We just saw that when you had 3 frames of memory, at least for this particular reference string, we got 9 page faults. I gave the process a little bit more memory to work with, and it exhibited 10 page faults. There's a name for this. Belday's anomaly says that having more frames of memory can yield more page faults. And this doesn't just happen in page memory, but this can happen at different levels of the memory hierarchy. The same thing can happen in cache memory that's caching what's in main memory. Normally you'd expect having a little bit more cache or having a larger cache memory is going to improve your performance. And in general, it probably is, but it is not guaranteed to. Sometimes, and in this case, for a carefully designed reference string, or I guess said better, for particular patterns of memory references, having a little bit more cache, or in this case, having a little bit more physical memory to host your pages, can actually hurt performance. So we're not the first people to notice this. Belladay's anomaly says this can happen, and it can happen at multiple levels of the memory hierarchy. It doesn't have to happen. You can build a page replacement algorithm that is immune to this anomaly. Stack algorithms, for example. A stack algorithm is one that has a particular policy for replacing pages. And because of that policy, it's guaranteed to not exhibit Bilott's anomaly. What's the policy of a stack algorithm, or what does it guarantee? I've written that on this slide. I wrote it 2 different ways because I think it's a simple idea. It's just a little bit hard to say. So the first way I'm trying to describe it is, if you think about a page memory system, you've got a particular set of frames of memory. Let's say you have F frames of memory. That's just the number of frames you have. At any point during their execution, you're going to have some pages in those frames of memory. If I gave you 1 extra frame of memory, or if I gave you more frames of memory, you're always going to have a superset of what you would have with fewer frames at every stage of execution. And that's what I say in this first one. The set of stuff you have in memory at any stage of execution with just F frames, that'll always be a subset. And here I'm saying it backwards, so that's why I'm saying subset. The stuff you would have in memory with F frames available will always be a subset of what you would have with F+1 frames. Down at the bottom, I try to say the same thing, maybe more informally. Having an extra frame will let you keep something additional in memory, but it won't cause you to throw out something that you would have had in memory if you had fewer frames. And as long as your page replacement algorithm follows that rule, it can't exhibit Bilott's anomaly. It can't reduce performance, because at every step of execution, it's still going to have everything it would have had with fewer frames, along with possibly some additional stuff that it's storing in those extra frames. I guess a takeaway from this is, obviously, FIFO, I'm looking back for, yeah, first in, first out, isn't a stack algorithm because it can exhibit this anomaly. FIFO is good and it's bad. The good thing about it, I think its best quality is it is really cheap to implement, kind of for 2 reasons. One of them I've already mentioned. If you look back at this last simulation we did, you'll remember every time we had to choose a victim, it was just really the next whatever's in the next frame. So we filled up the frames top to bottom, and then our first victim was whatever was in this top frame. And then our next victim was whatever was in this next frame. And then our next victim was whatever was in this next frame. And then whatever's in this next frame. And then when we got to the bottom frame, we just wrapped back around to the top. And the reason it worked that way is because we filled the frames top to bottom. So the oldest page in a frame of memory is always going to be whatever's in the next frame, whatever's in the frame after the one we just picked as a victim. So we can implement FIFO with really just a next victim pointer, just an index to whatever frame is right after the one that was just chosen as a victim. So that's computationally cheap. We don't have to look at what's in all the frames. We just step the next victim pointer to the next frame, and then that's our next victim. And we wrap around when we get to the bottom. And I guess even more importantly, this algorithm only has to run when a page fault occurs. When a page fault occurs, we step the next victim pointer, and that's our next victim. And then we forget about it until the next page fault. As long as page faults are rare, then even that small amount of overhead rarely happens. So FIFO is computationally cheap, it's easy to implement, and it only has to run when a page fault happens. But it doesn't make any effort to choose a good victim. And we kind of said that is the OS's, one of the OS's few tools to try to make sure a page fault rate is low. What could we do if we wanted to do better than FIFO? What could we do to try to choose a good victim? Well, we kind of saw this in the examples we were working. Often we would make, at least FIFO would make the bad choice of picking as a victim a page that we were going to need right away. Like often we would throw page 1 out of memory, and then the next reference to memory would need page 1. And that's kind of the worst choice. If you had to pick a victim, you don't want to pick one that's about to be used next. You really want to pick one that isn't going to be used again for a long, long time. And that is the idea behind the optimal page replacement algorithm. There's an algorithm, we're just going to call it OPT, O-P-T, like I've got over here. And that will be our name for the optimal page replacement algorithm. And it does what we just said. When it picks a victim, it chooses the page, whatever frame it's in. It chooses the page that won't be needed for the longest time. So it never, at least if it can avoid it, it doesn't choose a page that you're going to use in the next memory reference. It does the opposite of that, the one that won't be used for the longest number of memory references. This is provably optimal in terms of the number of page faults. So this algorithm is guaranteed to give you as few page faults as you could possibly have. At the end of a reference string, you could have other algorithms that, or other policies that tie with opt. So there are other choices you could make that might do just as well, but they can't do better. Opt is guaranteed to give you the lowest possible number of page faults. So let's see how it does. Here, same reference string as before. So this is the one that did badly on FIFO. And I'm pretending I have 4 frames of memory to work with. So if opt is really optimal, we know something about how well it's going to do on this reference string. What do I mean? Well, FIFO got 10 page faults using this reference string and these 4 frames. So opt better do at least as well as 10. It better not give us more than 10 page faults. And in fact, FIFO gave us 9 page faults when we didn't even have 4 frames, when we only had 3 frames. So if opt is really optimal, it better do at least as well as 9, because if it just didn't use this last frame at all, it could get, it should do as well as FIFO. Having this extra frame might let it do better. Let's see how it does. We'll do the same trick we did before. I'll just mark pages down as they get referenced, and then I'll scratch through them as they get replaced by other things. So initially, memory will pretend it doesn't have any of this process's pages in it. So when the process accesses page 1, we have to page fault it in, and then when it accesses page 2, and then page 3, and then page 4. And that was 4 page faults, but we'll just let this chart count them for us. And then it accesses page 1, woohoo, that's in memory, so that's not a page fault. Page 2, that's not a page fault. Page 5, now I'm gonna have to kick someone else out to make room for page 5, but opt tries to be smart about this. So I better not kick out page 1 because I'm about to access it. I better not kick out page 2 because I'm about to access it. I better not kick out page 3 because it's next in line. Well, page 4 is going to be accessed after that, but I've got to pick someone. And page 4 is the one that won't be accessed for the longest amount of time. So it's going to make the best victim we have. Let's throw 4 out of memory. to make room for page 5. Oops, sorry about that. To make room for page 5. And that cost us a page fault there. But we had to pick someone to throw out. So I'm going to say that was unavoidable. Fortunately, page 1, our next page referenced, is still in memory. Page 2 is still in memory. Page 3 is still in memory. So those aren't page faults. But now we got to pick someone else out to bring in page 4. Well, we better not kick out page 5 because it's about to be referenced next. But anyone else would make an equally good choice. So here it's kind of a tie. I'll just pick page 1 to throw out to make room for page 4. And that was a page fault. But at least now when we access this last page, page 5 is still memory resonant. So that's not a page fault. So that was only 6 page faults. Sorry, that's supposed to be a 6. 4 here and then 2 more here. So we did way better than FIFO did by trying to be smart about our choice of a victim. We can do some more examples. Normally, I would want to give you some practice on this. So I made up a longer reference string, and we'll make it a little simpler by dropping down to just 3 frames. So our examples will be a little bit shorter. And we'll try this reference string. I think I made this up, but it might be copied out of your book. But I think the important thing about it is it shows what memory references normally look like. That string we've been playing with, it was deliberately designed to exhibit Belladay's anomaly, at least for FIFO. This one is more of a random reference string, but it shows what processes normally do, and that is they've got some pages that are very frequently accessed, and they've got some other pages that are rarely accessed. Like here you can see page 0 is getting accessed a lot, and page 2 is getting accessed pretty frequently, but page 7 is rarely accessed. That kind of reference string, I think, would give us a realistic illustration of what algorithms perform well and which ones might perform poorly for a realistic process, one that has some pages that are getting used frequently and some pages that are less common. So let's try this string out with our 2 algorithms. I'll try and go through this faster because we've already talked about how the algorithms work. We're just working a couple of other examples here. So here, and I'll do the same trick. I'll use this chart to illustrate or to help me count page faults when I'm done. So for this reference string, we access page 7, page 0, and we're assuming memory initially doesn't have any of this process's pages in it. Page 1 with no page faults, or sorry, with page faults every time, but we didn't have to pick a victim to throw out. But then when the process accesses page 2, we're gonna have to throw out page 7 to bring in page 2, that's a page fault. When it accesses page 0, that's memory resonant, so that's not a page fault. When it accesses page 3, we're gonna have to throw out page 0 to make room for page 3. And then we access page 0 again, so we're gonna have to throw out page 1 to make room for page 0. And then when it accesses page 4, we're gonna throw out page 2 to make room for page 4. When it accesses page 2, we're gonna have to throw out page 3 to make room for page 2. When it accesses page 3, we're gonna throw out page 0 to make room for page 3. When it accesses page 0, we're gonna have to throw out page 0 to make room, page 4 to make room for page 0. When it accesses page 3, woohoo, that's memory resonant, so I don't have to throw out anything. When it accesses page 2, that's still memory resonant. When it accesses page 1, we're gonna throw out page 2 to bring in page 1. When it accesses page 2, now we're gonna have to throw out page 3 to make room for page 2. When it accesses page 0, we're going to, well, it's memory resonant, so we don't page fault. When it accesses page 1, that's still memory resonant, so we don't page fault. When it accesses page 7, we're going to throw out page 0 to make room for page 7. When it accesses page 0, we're going to throw out page 1 to make room for page 0. And then when it accesses page 1, we're going to throw out page 2 to make room for page 1. That's 15 page faults we had. I went through that quickly. I'll check after class to see if I made a mistake on that. If I did, I'll re-record just this example. Hopefully I didn't make a mistake on that. I didn't practice this example before class, but I'll double check that afterward in case I did anything wrong. But as long as I didn't make a mistake, now it looks like we had 15 page faults. Let's try out opt, because opt might do better. It certainly can't do worse. And if you were watching, there are probably some places where we could have made better choices for a victim. And opt is going to be able to make those choices. It's going to look for a victim that won't be used for the longest time. Still has to start out the same, because if initially memory doesn't contain anything for this process, when we access page 7 and 0 and 1, those all generate page faults. When we access page 2, who are we going to pick as a victim? Well, it better not be page 0. Moving on. Now, the next of the two that are in memory, 7 and 1, 1 is going to be accessed again here. 7 isn't going to be accessed until here, so 7 makes a better victim. So I'm going to throw out page 7 to make room for page 2. And then page 0 is already in memory, so that's not a page fault. Page 3 isn't in memory. Who should I throw out? I better not throw out 0 because it's about to be accessed. I better not throw out 2 because it's going to be accessed after that. So that leaves page 1. I'm going to throw out page 1 to bring in page 3. And then page 0 is memory resonant, so that's not a page fault. Page 4 is not memory resonant. Who should I throw out to make room for it? Well, I better not throw out page 2. I better not throw out page 3. So that leaves page 0. I'm going to throw out page 0 to bring in page 4. Now we're up to 6 page faults. Page 2 is still in memory, so that's not a page fault. Page 3 is still in memory, so that's not a page fault. Now page 0 we threw out a moment ago, so we have to bring it in. Who should we throw out to make room for it? It better not be page 3. It better not be page 2, so that leaves page 4. We're going to throw out page 4 to make room for page 0. So that was another page fault, but now we can access page 3. It's memory resonant. We can access page 2. It's still in memory. And then when we access page 1, we've got to throw out someone to make room for it. We better not throw out 2 because we're about to access that. We better not throw out page 0. So our victim is going to be page 3. We throw out page 3 to make room for page 1. And then, well, that was a page fault, but now we can access page 2 without a page fault. We can access page 0. It's still in memory. We can access page 1. It's still in memory. But then when we try to access page 7, it's not in memory. We got to pick a victim. It better not be page 0 because we're about to access that. It better not be page 1. So we're going to throw out page 2 to make room for page 7. And then that was a page fault, but page 0 doesn't cause a page fault, and page 1 doesn't cause a page fault. So here we ended up with only 9 page faults. And if you back up compared to what we had with FIFO, that's way better. We already said if this algorithm is really optimal, we can't have done worse, but here we ended up doing a good bit better. And normally, if we were meeting face-to-face, people would probably feel more comfortable interrupting me. I didn't get the usual interruption I get, but I planned for that on this slide. And the interruption I normally get is, can we really implement this optimal algorithm? Normally, I try to say something like, all right, we've got an optimal algorithm for page replacement. So why don't we just use that? And the answer is, because we can't. It's kind of like the optimal algorithm for CPU scheduling, at least in terms of waiting time. You remember that algorithm said, always pick the process that has the shortest burst length, or for shortest remaining time burst, that has the shortest remaining time on its burst. That required knowledge of the future, and so does this. To do opt, I was always whenever I had to pick a victim, I was looking ahead in the reference string to see what's going to be referenced in the future. And you can do that if you've got a reference string written down on a piece of paper, but If you were implementing this in practice, this reference string, we're pretending that is what the process is doing, what pages it's trying to access. And you can't know, at least in general, without simulating it ahead, you can't know what a process is going to ask for. The person who wrote the process might be able to tell you that, but for the OS, that's determined by what instructions the process executes. So I'm going to say there's not a good way to know for a fact which pages a process is going to need in the future. So it means we can't really implement opt, at least not perfectly. We had the same problem with CPU scheduling. What did we do there? Well, we assumed that past behavior was a good predictor of the future. And that's not guaranteed to be right, but I think it makes some sense. We could do the same thing here. Instead of knowing what a process is going to reference in the future, we could at least know what it has referenced in the past, and we could assume that's representative. And that's what least recently used does. It says, I may not know what pages a process is going to try to reference in the future, but I can know what pages it's referenced in the past. And pages that it's using very frequently, those are probably pages that it's going to continue to use frequently. Pages that haven't been used very much in the past, or I guess the right way to say this is pages that haven't been used for the longest amount of time in the past. Those make good victims. Pages that were just used in the past, those make poor victims, because maybe they're going to be used again in the future. And that's really where this name comes from. Least recently used. It says when I pick a victim, it's going to be the one that has been used least recently, the longest amount of time in the past. We could simulate this. We could use our original reference string and simulate it on 4 memory frames and see how it did. Instead, I would like to try this longer reference string. Same thing, let's assume we have 4 frames of memory available, and we want to simulate this reference string. Let's see how well least recently used does. Now, starting off is easy. We'll process accesses page 7, page 0, page 1, and page 2. And that was 4 page faults. But we couldn't have avoided that. None of our pages were in memory, so they all had to get brought in. Now, page 0 is not a page fault. Page 3. Now that's a page fault, it's not memory resonant, so we have to pick a victim. Well, we better not pick page 0, we better not pick page 2, we better not pick page 1, because again, now we're looking backward. Those are all pages that were recently referenced. Really 7 is the one that was referenced longest ago in the past. So we'll throw out 7 to bring in page 3. And then we reference page 0. Well, that's still in memory, so that's not a page fault. For page 4, now we got to bring it into memory. Who should our victim be? It better not be page 0. It better not be page 3. It better not be page 2. So that leaves page 1. We'll throw out page 1 to bring in page 4. And then when we reference 2, it's still in memory. When we reference 3, it's still in memory. 0 is still in memory. 3 is still in memory. 2 is still in memory. 1 is no longer in memory. So we have to pick a victim to throw out. It better not be 2 or 3 or 0. So we're going to throw out page 4 to bring in page 1. And then page 2 is still in memory, so that's not a page fault. Page 0 is still in memory, so that's not a page fault. Page 1 is still in memory, so that's not a page fault. Page 7 isn't in memory, so we have to pick a victim. Now, it better not be page 1. It better not be page 0. It better not be page 2. So that leaves page 3. We're going to throw out page 3 to bring in page 7. And then we can access page 0 and then page 1 without page faults because they're still in memory. So we get through this whole reference string. We had 4 frames to work with here, so we had a good bit of room. We ended up with, it looks like 8 page faults in this case. And it looks like we've hit the end of our time. Here's where we're going to stop. We did an example simulating LRU. The next thing we're going to talk about is how could we implement this? If LRU is an approximation of opt, how could we build this with help of the OS and of hardware? But we'll save that for next up. We'll stop here. I'll stop the recording, but I'll hang around if people have questions. And thinking ahead to next week's exam, we'll say where we just ended up. Being able to simulate LRU, that's how far we got. I'll update the study guide so it reflects topics just up to that, and I'll try and do that shortly after class today. I'll see you next week. Otherwise, if you have questions, hang around and I'll try and take those.